So, good afternoon, everyone. It was a long day, right? But we have only one more talk for today, and it's a very special one. So I would like to thank you, Professor Gandhi, for being part of our House Symposium this year. Professor Gandhi is a full professor at the physics department. I believe it's a theoretical and experimental physics department, right? At UFRN. I know that he's interested in complex system, and he has been collaborating with a lot of the researchers at the UFRN and from other universities outside. I just learned that a friend of mine that works at the Instituto Pasteur has been communicating with Gandhi. I mentioned to him. But here at the Institute, Gandhi is collaborating with Professor Draulio in his projects using psychedelics. And he's coming here today to talk about exactly the effects of psychedelics, higher order effects of psychedelics beyond pairwise interactions between cortical regions of the brain. So Professor Gandhi, thank you very much for taking part at our scientific celebration, our yearly celebration. The floor is yours. Thank you very much.
Thank you very much. So good afternoon, and thank you all for coming. Before I begin, I would like to thank the organizers for inviting me, and especially Kirsten Schmidt and Claudio Queiroz. The title of my talk is Higher Order Effects of Psychedelics Beyond Pairwise Interactions Between Cortical Regions of the Brain. And it's a line of work that was inspired by this paper from long ago, more than 10 years ago, that uses graph theoretical methods to look at propofol anesthesia. And this led to a PhD thesis and a paper that uses similar methods to look at what happens when people take ayahuasca. Aline was a PhD student of mine and Professor Draulio Araújo, and Elcio was a master's student. And what I'm going to show you today, the main result, is from an unpublished paper that we plan to submit soon, and it uses topological data analysis to look at higher order effects. So this is Thales, who did all the work with topological data analysis, and he was my master's student, and Fernando Santos, who was a mathematics professor in his CFI but got hired in Amsterdam, was the co-advisor. Elsie was another master's student. Rafael collaborates with Thales. This is Aline, who was my PhD student, co-advised by Draulio, and it was actually this collaboration that got me started into psychedelics. Fernanda is here. Fernanda and Eloisa work here at ICE. José Garcia Miranda is now the PhD advisor of Thales. So I'm going to introduce the problem, summarize the data, discuss an idea that some of you may know called the entropic brain hypothesis, and then I will show you some new results of higher order effects of psychedelics. So we want to understand what happens in the brain when we take psychedelics, and the main question that we were asking is the following. Graph theoretical methods, by graphs I mean standard graphs, so nodes and vertices connecting two nodes. They have been used to understand more or less how psychedelics change the functional connectivity of the brain. And we wanted to know whether there are any non-trivial higher order effects or whether standard graph theory is enough to describe everything. But if there are higher order effects, then we might need more advanced methods that go beyond graph theory, such as hypergraph theory. There are many reasons why these kinds of problems are important, not least the therapeutic potential of psychedelics, which Professor Draulio Araújo has studied, and some of the results are really amazing. There's also, of course, social reasons, sociological reasons why the problem is interesting, and many other reasons. So, usually my audience includes many physicists, but since here we're at a neuroscience conference, I'm going to skip introducing what is a psychedelic. But if you have never taken a psychedelic, this is a painting by this artist Pablo Amaringo that I like to show because it tries to convey some of the visual effects of some psychedelics. So the psychedelic that we studied is ayahuasca, and it is a beverage made from two different kinds of plants. One plant contains DMT, which is a tryptamine psychedelic, and the other plant contains compounds such as harmaline, which inhibit monoamine oxidase, and the two taken together allow a psychedelic experience of a few hours. But the main reason we use ayahuasca is that in Brazil, it is legal for religious and scientific use. Okay, let me summarize the data. These data are quite old, actually, and they consist of fMRI images, and the particular signal being analyzed is the bold signal of 9 adult healthy volunteers, and the scans were made before and after taking ayahuasca when they're awake and at rest. Let me now introduce or review the entropic brain hypothesis. And many of you may know the entropic brain hypothesis already, a hypothesis introduced by Robin Carhart-Harris about 11 years ago, I believe. But nevertheless, I would like to present this text because it really gives context to the hypothesis. So this is a quote by a British philosopher, which maybe many of you know, called Alan Watts. And this book, The Wisdom of Insecurity, is an incredible book which I highly recommend to anyone interested in these kinds of questions. And in this book, you can see a distinction. Alan Watts talks about a distinction between what he calls primary consciousness, and for lack of a better word, everything else, which would be secondary consciousness. So I would like to read this text very quickly because it goes to the heart of what we are interested in. The primary consciousness, the basic mind which knows reality rather than ideas about it, does not know the future. It lives completely in the present and perceives nothing more than what is at this moment. The ingenious brain, however, looks at that part of the present experience called memory, and by studying it is able to make predictions. These predictions are relatively so accurate and reliable, for example, everyone will die, that the future assumes a high degree of reality, so high that the present loses its value. But the future is still not here and cannot become a part of experienced reality until it is present. Since what we know of the future is made up of purely abstract and logical elements, inferences, guesses, deductions, it cannot be eaten, felt, smelled, seen, heard, or otherwise enjoyed. To pursue it is to pursue a constantly retreating phantom. And the faster you chase it, the faster it runs ahead. So here you see a clear distinction between what he calls primary consciousness, right? What we associate it with qualia, the felt sense, the lived experience, and all these other interpretations, constructed consciousness. So the entropic brain hypothesis distinguishes the ordinary state of mind from the psychedelic state of mind in the following way. The idea is that the ordinary state of consciousness has low entropy in a sense which I will explain, and the psychedelic has a higher entropy for the following reason. In the ordinary state, we have all these interpretations, social constructs, normative restrictions, and so on. You have a highly socialized human being. The mind has been trained, and so there are many constraints. For example, taboos. These constraints mean you have less freedom, fewer configurations that are possible for what is allowed, and so in this particular sense, we have an associated low entropy. In contrast, when you take the psychedelic, you revert to this primary state of consciousness. For lack of a better word, people use the word primitive human sometimes. The mind is more flexible, the possibilities are greater because there are less constraints, and in this sense, you have a higher entropy. So the entropic brain hypothesis predicts that in some sense, the entropy will be higher when you are in the psychedelic, under the influence of a psychedelic. Going back to our data, so we have these fMRI images of these subjects before and after ayahuasca. You can use standard atlases to define the cortical regions, and then you can calculate the Pearson correlation between pairs of cortical regions. And then you can try to calculate entropy in some way. So how did we do this? These are some old results. I'm just trying to give the background to why hypergraphs may be necessary. So once you have this Pearson correlation matrix, which is approximately 100 by 100 matrix, you can use thresholding to convert the Pearson matrix into an adjacency matrix. And so let me show this. So here you have a Pearson correlation matrix, and you can use a kind of thresholding where you put a 0 if the correlation is not strong, and you put a 1 if the correlation is stronger than some threshold, and so you can generate a matrix of just zeros and ones. So this is called an adjacency matrix. And adjacency matrices of zeros and ones are mathematically equivalent to undirected graphs, unweighted and undirected graphs. For example, this node 3 is connected to node 5. So if you look at this matrix, say line 3, column 5, or vice versa, you get a 1 over here. But 3 is not connected to 8, and so you see there's a 0 over here. So they're equivalent. So once you have the adjacency matrix, you can use network methods to calculate entropy. And this is somewhat of an art as well as a science, because the threshold has to be chosen carefully, and I won't get into the details due to lack of time. So let me show you one way to calculate entropy. Once you have the network, you can calculate the degree of a node. The degree of a node is simply how many neighbors it is connected to. So for example, this node has degree 3 because it has 3 other nodes to which it is connected. If you know the degrees, then you can make a histogram of the degrees and create a distribution for the node degrees. And once you have a distribution, basically a probability distribution, you can now use any functional of a distribution to calculate interesting properties. And one of them is the Shannon entropy of a distribution, which is a well-known quantity. There are other ways of estimating entropy, which I won't discuss. So let me, okay, so here's the summary of what we find. So after ayahuasca intake, we do find an increase in the entropy measured in this particular way, the Shannon entropy of the node degree distribution. And there are some other interesting results as well. But this result, the increase of Shannon entropy of the degree distribution, fits nicely into the framework of the entropic brain hypothesis. So this is the background to what I would like to show next. So I will skip all the details of the results. Now, we are interested in higher order effects. So I'm going to review some basics about hypergraphs. Hypergraphs are defined very similarly to graphs in the sense that you have vertices and you have edges. So in this hypergraph, there are 7 vertices: vertex 1, 2, 3, 4, 5, and 6. And there are even edges that are similar to the edges of a normal graph. For example, this orange edge connects vertex 2 with vertex 3. It only connects 2 nodes. However, this yellowish and this green edge connect 3 vertices. The yellow one connects vertex 1, vertex 2, and vertex 3. The green one connects 5, 6, and 3. So these are hyperedges. And hyperedges are not reducible to normal edges. You also have, for example, a one edge, which is just the node itself connected to itself. So these are hyperedges, and they can be represented in other ways. But the important point is that, for example, a 3 edge is not necessarily reducible to a number of normal edges connecting pairs of edges. There are many examples where hypergraphs are needed. For example, there are chemical reactions that cannot be represented by graphs but require hypergraphs. In physics, in quantum mechanics, hypergraphs are sometimes necessary to represent quantum states and so forth. There's a famous example of hypergraphs needed to describe applause, spontaneous applause, when someone starts clapping and it spreads and the whole group starts clapping. It turns out graphs cannot describe the propagation of this applause correctly. I have chosen this particularly simple example, which is a triadic, a love triangle, jealousy. So in this example, A loves B, B loves C, A is jealous. Now A may know C, A may not know C, but that's not the point. There's an irreducible jealousy that cannot be represented in terms of pairwise interactions. And the reason is that A is not jealous of B or of C. A is jealous of the link between B and C. So somehow A is connected to this interaction over here, and it's not reducible to graph pairwise connections. Jealousy is irreducibly triangular or triadic, and so graphs cannot model jealousy correctly, but hypergraphs can. And there are many other examples, like I said. So I hope it's very clear why sometimes hypergraphs are needed to model certain kinds of phenomena. Okay. Now, some of what I'm going to show you is some of the details of the mathematics are not real. We don't really need to understand all the math to make sense of what I'm going to say. So I would like to focus on the application to the brain, to studying these Pearson correlation matrices, and not on the very kind of abstract math. So a particular kind of hypergraph is the simplicial complex. And the simplicial complex is built in terms of simplices, or simplexes. And I think it's easier to explain what it is by example. So the 0 simplex is just a point. The 1 simplex is 2 nodes connected by the edge, by the normal edge. A 2 simplex is a triangular thing. It has 3 nodes, but the edge is a hyperedge. Now it's a 3 edge, and so this entire red area is part of the simplex. A 3 simplex is a tetrahedron, including the interior, and this would be a 4. This is the 3-dimensional shadow of a 4 simplex. And so these are very special kinds of hypergraphs they're sort of like, you can think of them as the atoms in a periodic table or something. You can make more complicated things by gluing together these simplices. So a simplicial complex is what you get by joining together these simplices. And we can construct simplicial complexes from our ayahuasca data. So this is what I'm going to show you next. These names are sometimes somewhat intimidating, homology groups and so forth, but I would like to point out that they have kind of very simple interpretations. So there are these quantities called homology groups that are topological invariants, and what that means is if you distort the shape, the quantity remains unchanged. So for example, a cube is topologically equivalent to a sphere because you can continuously deform the cube into a sphere. And the group H0, it measures the number of connected components. H1 measures the number of loops. For example, you can go around like this, clockwise or counterclockwise. H2 measures the cavities inside closed surfaces. And H3 would measure higher dimensional cavities and so forth. And these numbers, beta 1, beta 2, beta 3, that are called, beta 0, beta 1, and beta 2 are called Betty numbers. They simply count how many of these objects do you have. So for example, a cube is a single connected thing, so it has Betty number beta 0 equal to 1. There are no loops going around the cube, so it's 0. But a cube is hollow, so there's a space inside the cube, and so beta 2 is 1. For a donut, for example, you also have one connected component. You have one hole, which is the interior of the donut, where the bread is. But you also have two other structures, which are two circles. One is the circle going around the donut in this direction, and then you have another one that goes around the torus in the other direction. So these are all topological invariants, and we can look at topological invariants for simplicial complexes built from our ayahuasca data. How do you do this? So you take your Pearson correlation matrix, define a distance, because we need distance to relate the nodes. Then we use thresholding to create edges or hyper edges or whatever, where if the two nodes are within the thresholding distance, then they are labeled as connected. And then you can look for topological invariants. And in our case, we looked for these topological invariants I just showed you, which are the homology groups. Once we have them, we can see how they are born and how they die as we change the thresholding. I will show you this in just a minute. And from this, we can calculate another kind of entropy, which is the entropy of the persistent homology of these H0, H1, H2, and so forth. And this recipe for data analysis is known as, it's one approach to topological data analysis, TDA. I will skip the mathematical details and show you an example. So imagine that you have put your data, you have defined your distance between the points, and these blue circles are actually blue hyperspheres in some space. And we're going to increase the size of the radius. So here you see the circles are small, here they're bigger, and here they're so big, all the nodes are inside the circles. Now here, as you can see, the radius is small, and very few of the nodes are connected. But if you increase the radius, more of them start to become connected. So for example, this node here is disconnected. Here it's disconnected. Here it's disconnected. But here it's already connected. Now what happens eventually is that this 2 edge is a normal edge connecting 2 nodes. It will die because it will become part of a hyperedge. And so you can track the birth and the death of edges and hyperedges. So these are the results for ayahuasca. So here is the radius of the hyperspheres that I was mentioning. And this, what this graph shows is when a particular structure is born and when it dies. And I think they have been sorted with the death radius. So for example, let's take this first structure over here, or rather, let's take the very first one over here. So this, when the radius is just below 0.5, is when this particular cavity, because this is the H2 homology group, so that means the cavities, a cavity is born, and as the radius increases, it persists until about 0.7, and then it dies, because it becomes part of a higher order structure. For reasons that I don't wish to explain, very, very short bars represent noise. This is a known result. Whereas large bars, such as this, represent genuine topological structure. Now, this kind of graph is a standard way of analyzing data using TDA, and it's called a barcode. And as soon as you have a barcode, you can immediately calculate a number of other quantities. One of the quantities you can calculate is called the persistent entropy. So what you do is you just take those bars, the lengths of those bars, treat it as a weight, normalize the weight so that their sum is equals 1. These normalized weights can be interpreted as a probability, and you calculate the Shannon entropy as before. These are the results for ayahuasca, and what we find is something fascinating. So the entropy doesn't increase, it decreases. And we actually thought maybe there's a bug in the code, but this seems real. Let me wrap it up. So the increase in the Shannon entropy of using normal graph, standard graph theoretical methods was in line with the entropic brain hypothesis. But now we have these new results which seem to show exactly the opposite, but only for the higher order entropies. And like I said, these are preliminary results and they need to be reproduced independently. But we are confident enough that we're going to submit these results very soon. And so we can ask, let's just assume this is correct, right? Let's assume that we have found a genuine, real result that's not a bug or some other artifact, and ask, what could it mean? So let us allow ourselves, or rather you allow me to speculate what this might mean. And I have had a long-standing fascination with phenomena that cannot be reduced to the standard simple ways of understanding phenomena. So I've made a sort of career out of doing this. And in this particular case, I would like to point out that maybe we have found something that is genuinely a higher order. So, the Greeks thought that they were shocked when they found out that the square root of 2 cannot be expressed as the ratio of 2 integers, right? Because real numbers are not always reducible to rational numbers. And there are many other examples, and hypergraphs are not always reducible to ordinary graphs. So could it be that some processes, some cognitive processes, cannot really be explained with pairwise relationships, graph theoretical methods? And if this is true, then maybe what is happening is that psychedelics, even while they sort of scramble the pairwise interactions, and maybe give us very interesting experiences due to the scrambling, maybe at the same time that they increase the entropy of these pairwise connections, maybe they're strengthening higher order structures in the brain, kind of hyper edges. And those of you who have had experiences with psychedelics will relate to me when I say, so my wife and I took psychedelics for the first time more than 15 years ago, and then we took it a few more times, many more times. And while at the same time there are very interesting things that happen, sometimes you come out of the experience with this feeling that you really had a really deep experience, something almost inexpressible in the standard language, very difficult to translate into language. And this kind of difficulty in translation also exists between languages, right? For example, in the Portuguese word saudade is very difficult to translate into English correctly. There's no single word, and if you do try to kind of make a paragraph to explain what saudade is, it sort of misses. It doesn't really work. There are other examples, for example, Yiddish nachas, for the pride we have in children. So these are untranslatable words, or difficult to translate words, and it could be that it has to do with higher order effects of that give depth to the experience, sort of like the difference between knowledge and wisdom, lower order effects versus higher order effects. So I will close with this thought, and now thank you very much.
Thank you, Professor Gandhi. Very, very thoughtful presentation, very provocative. So I open to questions. Anyone? Question? Yes.
I really like to talk. This is a very new concept for me, this hypergraphs and these edges that they're more like groups, right? Because you have 2, 3, 4 vertices in an edge. And basically, it's hard for me to even put this question to you because this concept is kind of new. But I'm trying to develop some intuition for what your result means. So pairwise interactions are getting scrambled. The entropy is increasing. But there is some kind of the entropy in these higher order things is decreasing, meaning there's some kind of consolidation happening. But where? Like, what does it mean higher? Like, if I look at this picture, do you mean instead of pairwise interactions between 2 brain regions, there's something like, let's say, E3, which is a collection of 3 brain regions, and that interaction is getting stronger, some kind of a 3-way interaction, but you're getting the data for that based on simultaneous recordings of each individual one. So it's not pairwise, but it's somehow 3-way of these 3 regions is being strengthened, even though the pairwise. I'm just trying to gain some intuition for what this higher order means here.
Okay. So this is an excellent question. No, what does it really mean, right? So we are now going to study the same thing again, maybe even with this data set, for the following reason. So this idea of using this persistent entropy calculated from the barcodes is standard practice in TDA. But there's a problem, which is the following. It's based on the Pearson correlation matrix, right? At the end of the day, we calculate these things from the Pearson correlation matrix, and guess what? The Pearson correlation matrix is pairwise. So all the higher order information that we are studying here or detecting is actually inferred from pairwise correlations that are contained in the Pearson matrix. And so we need to do this again, not using persistent entropy, but using a generalization of the mutual information. Mutual information is usually studied in terms of pairs, but it is possible to define mutual information for more than two to quantities. And so then we can basically do TDA, but with mutual information. So that's a big challenge, but since persistent entropy is what is the kind of standard practice, we went ahead with this anyway. But we really have to look at the higher order effects through genuine higher order tools. Now, but assuming they exist, your question of what does it actually mean? So it's as if the pairwise connections are becoming more disordered. So you have disorder, you have more flexibility, more number of configurations and so forth. But at the same time, these higher order structures have less freedom, less variability, less disorder. They become more ordered. So this would be the interpretation. Now, why, or what is the meaning, higher meaning of this? I don't know.
I have 2 points. One, a little criticism, and is the following. You always talk about brain regions, but you never specify which brain regions. And this is my criticism. And I have a question. And the question is, you propose a framework for understanding high-order problems. Do you think we could deal better using your framework to explain, for instance, the problem of decision-making, the problem of free will?
Wow. About the criticism, I think that's valid. However, I'm not a specialist in these brain regions. I know relatively little, but I can ask my collaborators. Maybe is Draulio here? Yes. So I don't know, Draulio, if you want to say something, but meanwhile about free will and so forth. I mean, this is a fascinating idea because as a physicist, in physics, we only know two kinds of dynamics: stochastic dynamics and deterministic dynamics. Everything else is a mixture of these two. And free will doesn't fit into either of them, because if the dynamics is random, it's not really free will, it's just random. But if it's deterministic, then it's predetermined, so it's also not free will. But once you allow yourself to think in terms of higher order effects, in fact, there's actually a type of theory of consciousness called higher order theories of consciousness. And so they try to explain qualia and consciousness as a higher order cognition. Not just, I think we're used to thinking in terms of meta-cognition, but maybe there are other kinds of higher order cognition in general, and that somehow consciousness has to do with higher order cognitive processes. And maybe free will can be explained like that, but I don't know. It's a fascinating question.
Yeah, more questions here.
Hi, Gandhi. Thank you very much for your talk. I mean, I have a comment and a question, because at the end of the day, entropy is a function, right? It's going to get any probability distribution and lead to a real number, whatever, whether the distribution is uniform or polarized or centered. So my question is, because here we talk, I mean, I understood the idea of the entropic brain and everything, but then I caught me wondering, because you computed entropy for this particular distribution of, say, the Barkhouse duration, but couldn't there be other distributions? I mean, who says, I mean, this is the most important distribution that relates to the theory of the entropic brain, as opposed to other metrics that could be calculated that would also have distributions?
Excellent question. So for example, we could have looked at the degrees of the hyperedges. So this would be the natural generalization of the node degree distribution. And in fact, in the community of people who study hypergraph, there's a big kind of debate or kind of rival approaches. Ones that prefer to use simplicial complexes and look at barcodes and so on. And then another school of thought, which is that we shouldn't look at barcodes and simplicial complexes. We should look at hypergraphs themselves, not worry about simplicial complexes. So this is a very valid question. And so why did we use barcodes? For a very practical reason. So one of our collaborators is an expert in using barcodes and made his career using barcodes. So it was the first thing that he said we can apply immediately. However, I personally am very interested in look at the degree distribution of hyper edges. So this would be the natural parallel of the node degree distribution.
Thank you.
I would like to follow up on that question. So if I understand this entropy hypothesis a bit, yeah? It makes sense to me if you're talking about the entropy of brain states. Okay, none of the statistics that you're looking, as valuable as they might be, are about brain states. They are about some correlations between huge ensembles of brain states. And then you're talking about higher orders. So you should look at 3-point correlations, 4-point correlations. You can take time into account. That would start to address the manifold of brain states to which your entropy hypothesis relates. So none of what you're doing has anything to do with this entropy hypothesis, right?
Yeah, the entropic brain hypothesis was originally proposed not in terms of functional connectivity, but in terms of the number of configurations of possible brain states. So this was the original idea. But it inspired many different ways of interpreting entropy. So for example, in Aline Viol, who was our PhD student, she looked at the Shannon entropy of the node degree distribution, which may not have been what the authors of the entropic brain hypothesis had in mind initially. Regarding the higher order, what you said, looking at 3-point correlations and so on. So this would be the higher order generalization of the Pearson correlation matrix, which is only a 2-point correlation measure. So like I said, the correct way to go forward is to look at not the Pearson correlation matrix, but use these other ways of measuring correlations that do involve 3 or more regions of the brain. The mutual information, the generalized mutual information for more than 2 cortical regions would do the trick. But if you want a linear correlation, then you can use standard 3-point or 4-point correlation functions that are exact generalization of the Pearson correlation.
Hi. So there are some evidence in animal experiments suggesting that psychedelics can decrease the coupling of the neurovascular unit. So in this case, the MRI is not like a good signal for measuring what you want to see, And Draulio has some measurements of EEG during the trip, right? So my question is, do you think if you analyze the EEG signal, then you would find the same thing that you're finding in the MRI?
Excellent question. Drau, in collaboration with Draulio, separate from this work, we are looking at EEG data, but we're not looking for higher order effects yet. Maybe this can be done in the future, but I don't know what we would see in the EEG data. In fact, this is all kind of very new to us. We were actually expecting the persistent entropy also to go up exactly like predicted by the entropic brain hypothesis. So that's why we were surprised by this result. So global versus local, right? This fascinating question. I know relatively less about the local effects, or for example, these vascular effects. I don't personally know very much about these things. I've never looked at, for example, spiking data on and so forth, but I would be very interested to look at it.
Okay, thank you for the talk, Annie. I want to follow up also. I had another question, but then I was inspired by your question and about the brain regions. So of how many nodes are we actually talking about? So I know that for doing functional connectivity matrices in fMRI, you have to put nodes together because usually you would have too much edges to, and then I imagine, although I have difficulty to translate this to reality when it comes to higher order, more than 3 or 4, probably the more nodes you have, the more dimensions you get in there, right? And then how many nodes are we talking about?
I was trying
because
to
with the
get
EEG,
the slide.
like to do suggested would be 64 maximum, yeah?
The slide is not working, but I can tell you the Pearson matrices are approximately 100 by 100. I think it's 104. 104 by 104. So everything is done on top of these matrices,
Okay.
104 by 104.
Okay, and then the actual question which I had was, this is now from before and after ayahuasca, and then it's about brain states. Did you try to use it on kind of control data, looking at this, just to get a better idea of what it could mean functionally of a normal resting state where there's no application of ayahuasca? And where's the same time in between? Because you have spontaneous fluctuations in resting state. Right?
True.
And you could have ups and downs in the
No,
holes in
for
the
this
matrix.
data set, there was no control.
From other, maybe there.
For example, the scans were only before and after.
Okay,
There were
so
no.
it's the only data set you applied this kind of method to.
For this method, this was the
there
only.
could be downloadable data, and
Yeah.
I was
Yeah,
just
we can.
trying to
we should do
understand
that.
what this means. Yeah.
Drauli, do you
That's
have
like a
any
short
comments?
circuiting, yeah.
Yes, okay, thank you. So the first one regarding the brain regions. So basically you have this atlas, and then you just have different segments, 104 segments that are averaging out a number of pixels in that area. So it's not a specific brain area, it's more of 104 areas throughout your brain that you do a pairwise correlation between the average of these spatially filtered signals. You see? Okay. Right, yeah, right. The second comment is regarding the neurovascular coupling. So basically what we do is we remove global signal. So this is one technique that you do in order to average out the global signal, and then when you do the correlations, they're pretty much normalized. So this is one way to circumvent. And then as we do have a kind of a control group, which is the baseline. So when we do the baseline are the individuals not under the influence of ayahuasca. So there is a control resting state group, so to say. But then it's the opposite. So you have an increase, right? Not a decrease. Okay. Yeah, okay.
Drauli, what about this idea of using downloaded data as a control?
That's another possibility. But we do have the control. So we don't have the placebo, which is a bad thing of this data set. And then I do have a question that's related to a possible interpretation of the entropy, which would be a problem in the data set that we are using a priori, that the pairwise kind of gets rid of it, which is the spatial correlation that we have for adjacent nodes. Because if we do pairwise, we are controlling how this spatial filtering or spatial correlation influences the data set. So if here, from what I understood, if you have a higher spatial correlation, then basically your hyperspace here will have more vertices that are related to the, to the spatial correlation, which in the pairwise we get rid of it because it's pairwise. So it doesn't, it's always pairwise. So the other one, it's not necessarily pairwise. You have some, there are 2, 3, 4, 5, so the number of nodes that you include in each hyperspace, so to say, it might vary depending on the spatial correlation, I guess. So that might be one way to think of why the entropy it would be different in these two configurations. It might be because of the data set. Because one thing I remember, which is a big issue, it's the number of nodes that we have. Because we are right at the edge of considering that a complex system, right? I mean, it's 100 elements. 100 elements is a very low dimensional system. So in other words, it might be that when we go in this hypergraph, then the low order of the graph that we are working on might be influenced somehow because we are right at that edge of the number of nodes that we are analyzing. So.
Yes. I hadn't thought about this, so we can talk later. Thank you.
So I will make the last question, if I'm allowed to. I know that we are out of time, but I understood that you measure before the ayahuasca experience and 40 minutes later. And then you show a beautiful graph showing that all participants, they decrease their entropy, right? So
most of them.
I saw that there is one subject that was very low entropy by default, but it also reduced. So it's two questions, in fact. The first one is whether the delta of the change in the entropy is associated with some mental experience, of subjective experience, or the duration of the experience and whatever. And the second question is somehow related to that. Do you expect, if you have the data set, that I believe you don't, but if you, let's say that you measure for 20 minutes, in 20 minutes bin, so you separate your data set for 2 hours, for example, in 20 minutes bin, and do your calculation, do you believe you will see, let's say, a decrease in entropy and then a return of the entropy as the substance wash out, or what's your opinion about it?
Yeah, so I can answer the second question, but I can't answer the first question because I don't know. Although I think Draulio will know, because I think some questionnaires were given, but I don't remember. But the second question, yes, I do expect that after enough time, the values of any kind of entropy that you measured will go back to what they were before. With ayahuasca in particular, some of the effects last on the time scale of a week. You know, some biases, some very small cognitive biases persist for 1 to 2 weeks after a single dose. But I don't think that they're strong enough to affect the entropy measures. I think they're very small residual effects having to do with some other mechanisms.
So the long-term effect of ayahuasca will not be grasped by this measure, right? Because
I don't think so. Okay. I think this only looks at the psychedelic experience itself.
Okay.
That's what I think.
Okay.
I'm not sure.
So Thank you very much, Professor Gandhi. It was a pleasure. Immediately, right, Sergio, at the library. So whoever is going to play a chess tournament after 10 hours of scientific talks, you deserve a prize. So see you tomorrow at 8:30. And for those who has a poster, tomorrow poster, please send your data bleed so we can have a small session of data bleed so you can practice your English. Thank you very much for everyone and see you tomorrow.